Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 50, and this problem asks us that when we look at the reactivity of this molecule on the top, we see that it's going to react with electrophiles to afford ortho and para substituted products. However, when we react this molecule with electrophiles, we afford meta substituted products. It asks us to explain the following observations. So what we know about ortho and para-directing substituents is that they are due to the fact that the substituent that's attached to the benzene is electron donating. However, what we know about meta-directing substituents on benzene is that the fact that they're meta-substituting is because of the fact that the substituent is electron withdrawing group. So we know about electron with donating group is that they make your benzene ring more electron rich, making it a better nucleophile. So we attack at both ortho and para positions. However, on meta-directing is the fact that the substituent makes the benzene ring a worse nucleophile, but making it more electron poor. So let's look at the identity of the atom that's directly bounded to the benzene ring in the top one. So we have this alkyl group here. So we know that the alkyl group will stabilize the positive charges on your ortho and para position due to the electron inductive donation of this electron cloud around these molecules. So here we have carbon and 2 hydrogen, carbon 2 hydrogen. So these all have electron clouds around them. So you can think of this electron cloud donating inductively into your benzene ring. So this increases the electron-rich nature of your benzene ring, making it a better nucleophile. So because of that, we know that R groups, or alkyl groups, what we call them, are electron donating. Because of that, they will direct substitution at the ortho, the 2 ortho positions, and the para position indicated here. Well, what about this molecule? Here we also have an alkyl group, an R group, what we call it. But this R group is not an sp3 hybridized orbital, it's sp2 hybridized orbital and has a pi bond. So if we actually do some resonance structure with this pi bond, we see that we actually get a resonance structure that now puts a positive charge on this carbon atom that's directly bounded to this benzene ring. So because of this positive charge on the benzylic carbon here, it is actually going to cause very unstable intermediates when this benzene ring reacts with electrophile. So if you were to react this with electrophile, for example, here, then what you see is that what we see is that now the electrophile added in the ortho position, but now this positive charge, if we do some resonance, will end up being localized right next to the positive charge on the benzylic carbon. So now we have a positive charge here, positive charge here. So we have 2 positive charges that are right next to each other. So this is extremely unfavorable and highly unstabilized. So because of this, this molecule will avoid at all possibilities to have these 2 positive charges right next to each other. So that's why it is not going to allow any ortho or para substitution to occur. It's only going to allow meta substitution to occur such that these 2 positive charges will not occur on adjacent carbons as shown here.